Alright, we are back. So this is the last of the videos that will be recorded out of this Forced Twig note pack. So the thing that I'm going to be interested in this video is the following idea. So let's suppose you have some gear. There it is. There's some wheel or gear that's spinning around. There are two different ways that you could measure the speed at which it's spinning. You could say, well, I'm going to wait a second and see how big an angle it traces out. Pause some unit time. I said seconds, but it doesn't matter what units you're measuring time in. That's one way that you could measure how quickly an angle is spinning. On the other hand, you could imagine that there's like a little bug here, a little bug on the edge of this circle that's spinning around. In that same amount of time, how much distance does that bug cover? So how much arc length gets traced out per unit time? So there are two different ways that you could measure the speed of a gear. They're both clearly related. If you're spinning a wheel faster, you'll cover more distance. So let's just write both of those down. So the angular speed of rotation measured in radians per second or any other unit per second. Radians, it could also be measured in degrees per second. Or in fact, revolutions. Pick your favorite way of measuring the angle, is given by omega, which is just how big an angle in radians is traced out per unit time. The linear speed is given by how much arc length a point on the edge of the circle traces. There, now that looks more like edge of the circle traces per unit time. So let's try to explore the relationship between these things. So suppose I give you a gear of radius 1/3 feet. So here's my gear. If I can't draw a circle, there's no way I'm going to try to add in the little teeth to make it look more like a gear. Let's suppose that its radius is 1/3 of a foot. And let's suppose it's spinning 2 radians per second. So, no, let's use a different color. Suppose it's spinning at a rate of 2 radians per second. So in 1 second, what's the radian measure of an angle that gets traced? Well, if it's spinning 2 radians per second, you wait for 1 second. Well, maybe I can write it out. 2 radians per second times 1 second. Well, that's just 2 radians. So in 1 second, you trace out an angle of 2 radians. How large is the resulting arc? Well, we have a formula for arc length. The arc length is equal to the radius times the angle. So that arc length, S, is the radius, is 1/3 of a foot, times the angle, which is measured in radians, so we don't need to do any converting, is 2. That's 2/3 of a foot. And it took 1 second to achieve that. So in 1 second, the arc length that's traced out was 2 thods of a foot. But in fact, this picture right now is dishonest, because this indicates that this is radians per second. This just says feet. So that's what happens if you wait for 1 second. So what's the linear speed? The linear speed, well, was 2 thods of a foot, and it took 1 second. So it's 2 thods of a foot per second. Or you could say 0.666 repeating feet per second if you prefer. Also, there's something interesting here. We could have done this whenever. It didn't matter that we started with this radius of 1 thod feet and the thing spinning at 2 radians per second. We could have done the same analysis, gotten a different answer, but the same analysis. That tells you that there's some relationship between the linear and angular speed. The linear and angular speed are related by the following formula. The linear speed is equal to the radius times the angular speed, where, let's just label everything. V is linear speed. Omega is angular speed. For emphasis, because it's very important that you do it this way, it needs to be measured in radians per time. It doesn't matter what the time unit is, but it does matter that you measure in radians. If you're measuring in degrees per second, you'll need to convert to radians per second. And of course, the radius is exactly what it should be. The R is the radius. Well, you could have done this all in degrees, and it would have been fine. You could have done it in revolutions. It would have been fine. But all of your formulas would be off by the fact that you would have to convert to radians to make this step walk. That step only walks if you're walking in radians. So you can still do stuff like this whenever. You just have to convert to radians first. So let's do an example. Let's suppose I give you a gear of radius 5 inches, spinning at 6 revolutions per minute. Let's compute the linear speed. So a picture is maybe helpful. So you have this gear. Its radius is 5. It's spinning at some rate. It's spinning at 6 revolutions per minute. So that 5 is the radius. Omega is 6 revolutions per minute. So it's not in radians. We'll have to convert. We want to know the linear speed. Well, we have a formula. We have this formula. But that formula only works once we have the angular speed in radians. So let's compute the angular velocity in radians per minute. So let's do that. Well, we know how to do that. 1 full revolution is 2 pi radians. So you know a total of 6 revolutions per minute should be 6 times 2 pi radians per minute. So the linear so that tells me that the angular velocity, omega, is 12 pi radians per minute. Now I can use this formula. I have omega, 12 pi radians per minute. I have the radius. The radius is 5 inches. So, figuring that all out, the linear velocity is 5 inches. That's the radius. The radius times the angular velocity. that's 12 pi. And I know here, for emphasis, it says radians per minute. But radians are in fact a unitless measure. That radian just tells you that the ratio of arc-lengthy things to angular things is 1. So now I have everything I need. 5 times 12 times pi is, I guess, 60 pi inches per minute. Nice. Let's suppose I give you a gear of radius 2 spinning at 30 degrees per minute. So we'll do the exact same thing. I know the radius is 2. I know the angular velocity is 30 degrees per minute. But degrees are no good, I need to convert to radians. So 30 degrees per minute, I need to convert that to radians per minute. And that's easy to do, right? How do you convert from degrees to radians? Well, you use the fact that pi radians is the same thing as 180 degrees. The units of degrees will now cancel. And so you wind up with 30 times pi over 180 degrees per minute. And that should obviously be simplified. So that's the same thing as 3 over 18, but 18 is 3 times 6. So that's pi over 6 degrees per. The whole point of doing this was to convert to radians, so it better be in radians. Alright, so there's my omega. Now I can use this formula to find the linear velocity. The linear velocity will be given by linear velocity is equal to radius times omega. I know the radius. The radius is 2. Whatever the units of distance being used are. And the angular speed, omega, is pi over 6 per minute. So, you simplify this all out, it looks like you get pi over 3, and I'd be happy writing this as 1 over minute. No unit of distance is specified. If you're more comfortable making up a name for a unit, pi over 3, whatever the units being used are per minute. Nice. So, another thing you can do is, let's suppose you understand one gear, and it's connected to another gear so that their teeth line up. You should then be able to understand the other gear because it should have something to do with the first. Let's be explicit. So here's a gear that we just walked out. It has radius 2 spinning 30 degrees per minute. So that's the gear that the same picture as above. So take this same situation and put it down here. So let's suppose you start with that same gear of radius 2 and angular velocity, which we just computed, pi over 6 radians per minute. And we computed its linear velocity, so we may as well write that. The linear velocity of this gear is pi over 3. So I just copied down the information above about this gear of radius 2. Let's suppose that that gear is connected to another gear of radius 1. So it's connected to a smaller gear of radius 1, so that both of these gears will have the same linear velocity. If you care about sign, they'll be spinning in opposite directions, but that would be like worrying about the difference between velocity and speed. I'll just suppress that. We'll just remember that they're spinning in the opposite direction, clockwise as opposed to counterclockwise. So they have the same linear velocity. So this little gear has a radius of 1, that's given, and I know its linear velocity. Its linear velocity should be the same as the other gear. So this has linear velocity equal to pi over 3. I'll suppress the units at this point. That's enough information that I should be able to figure out the angular velocity of that little gear. So let's try to figure out the angular velocity of the little gear. Well, let's go through and do it. So I have this formula that v, the linear velocity, is the same thing as the radius times omega, the angular velocity. And let's just write down the things I know. I know that the linear velocity of the little gear is pi over 3. I know what the radius of the little gear, the radius is 1. I would like to know omega. Is that an equation that you can solve for omega? Yeah, of course it is. It's basically already solved. You end up with omega equal to pi over 3 radians per minute. So this smaller gear has angular velocity of pi over 3 radians per minute. So what's the takeaway? The takeaway here is if you have some gears that are connected to each other via, well, this is by having their teeth line up, or if you have two wheels that are connected by a pulley belt, so that they have the same linear velocity, then as you learn things about one of the gears, you can learn things about the other gear. And there's one last example that I think I want to do. Let's suppose you have an automotor. It's driving 45 kilometers per hour. Its wheels have a radius of 40 centimeters. Let's try to determine the angular velocity of the wheel, and because often if you have a wheel spinning around, you have an automotor, you're worried about its angular velocity in revolutions per minute. So let's try to do that. And for emphasis, the main point of this problem is this issue, to be careful with units. So let's try to write that all out. So the car is driving 45 kilometers per hour. So let's draw a not very good picture of this situation. So there's the wheel. Just draw the front half of the car. It's driving forward at 45 kilometers per hour. Now, as you might know about cars, the thing that pushes a car forward is the fact that its wheel spins around. So that means that the linear velocity of this wheel is 45 kilometers per hour. Oh, neat. So that means I know the thing that's called V. Now, what else do I know about this wheel? Apparently, this wheel has a radius of 10 centimeters. This wheel has a radius of, oh, no, not 10. 40 centimeters. I would like to know the angular velocity of this wheel. Great, so I have a formula. I know that V is equal to R times omega. So that means 45 kilometers per hour is equal to the radius times the angular velocity. I can solve this for omega. 45 kilometers per hour times 1 over 40 centimeters is equal to omega. All right, well, there's obviously lots of unit mismatch that you can tell here because the units have been kept track of. It's all in metric, so that means that unit conversion is pretty straightforward. Let's convert kilometers and centimeters to meters. So 1 centimeter is 1/100th of a meter, hence the centi, or 1/100th. Of 45 kilometers, or 1 kilometer is 1,000 meters. And now you're in a situation where the units will cancel. So, you know what? There are two perspectives that one could have here. We could bust out a computing machine and do that computation. And maybe that's what you're tempted to do. But because I think sufficiently many people really struggle with division, let's do this division by hand right now. So, doing that. So I'm dividing by a thing that's less than 1. I'm dividing by 0.4. So in order to make the division doable, I think what I'll do is I'll multiply and divide by 10, make this 10 times bigger, make that 10 times bigger, and I'll wind up with 45, now followed by 4 zeros, divided by 4 times 1 over 1 hour. Eventually I'm going to have to convert from hours to seconds, but let's do this first. And I guess you want to do division? Let's do long division. So that's how many times does 4 go into that? Well, right, just you have to do it. 1, 1, carry the 1. 4 goes into 10 2 times, carry the 2. 4 goes into 25 times. So that will give me 112500. And this is right now in radians per hour. That's not the unit that I wanted. I wanted revolutions per minute, RPM. So let's do the more conversions. How many minutes to an hour? One hour is 60 minutes. Right now it's in radians. I need to convert to revolutions. 1 revolution is 2 pi radians. And before I continue, I'll decide whether or not I want to do this by hand or by using a computer aid. So clearly there will be like an issue with this pi. Let's decide first if it's even worth doing by hand, figuring out if, well, I see a 6 there and a 2 there, so those two will cancel. This will become just like a 30, and it'll cancel with that 2. No, that's a 1. So in order to see if this goes into that, let's see if 3 goes into this, because 3 is easy to test if it goes into. Just check if all the digits add up to 3. 1, 2, 3, 4, plus 5 is 9. Yeah, 3 does go evenly in. You know what, though? I'm going to... Okay, that's enough computation by hand. So, let's check that the units cancel correctly. Hours cancel. Radians cancel. I do wind up with revolutions per minute. Let's do this next computation with a computer aid. All right, and we are back. So, there's what we had. 11, 2,500, 112,500. Revolutions per 60 times 2 pi minutes. Doing that computation using a machine, 2,500 divided by 60 times 2 times pi is approximately 298.4 revolutions per minute. Great. So we'll stop there. I hope you're enjoying these videos.